Today's presentation will be about the seismic performance of reinforced concrete columns strengthened with ultra-high performance fiber reinforced concrete, or UHP FRC. Starting with the presentation outline, I will present the objectives of this presentation. After that, the introduction and problem definitions, which are related to the reasons of deficiency of RC columns, will be presented as well. As the third point, I will present the main components and the mechanical strength of the UHP FRC. After that, I will jump to the to show you how the UHP FRC was incorporated for strengthening applications in RC columns, and to see whether UHP FRC is a viable option or not. As for the fifth point, I will discuss the shortcomings of using UHP FRC in such seismic strengthening applications. And after that, the research gaps will be posted to see what can be done in order to make this material a better option for seismic strengthening applications. So first of all, as the first objective is to introduce why the columns are experiencing seismic deficiency. After that, I will explain if the UHP FRC is better than the normal strength concrete for seismic upgrading of reinforced concrete columns. After that, the main components and the mechanical strength of UHP FRC will be discussed and presented based on the several research works done before. After that, a trace of research works who incorporated UHP FRC in their seismic strengthening applications will be shown to see how the UHP FRC greatly enhances the seismic performance of reinforced concrete columns. After that, the shortcomings of this material for such applications will be explained, and which will introduce us to the research gaps that should be demonstrated in order to be addressed in the future to make this material a better option. So in structures, RC columns, in structures that resist earthquakes, RC columns are very important in resisting the earthquakes. However, therefore, their deficiency, if they possess a certain seismic deficiency, the collapse of the entire structure might be triggered, as we can see from Figure 1. Even the deficient RC columns didn't collapse, they can still sustain severe post-earthquake damages that require a substantial amount of money to repair and restore their original capacity. The reasons that the RC columns are seismically deficient is they don't have the adequate ductility to experience large displacements, or they don't have the sufficient lateral strength to resist the earthquakes. And the reasons behind that is their concrete core, or the concrete in general, they are not sufficiently confined, or there's an insufficient splice length, or the reinforcements, the longitudinal reinforcements are corroded. Maybe they don't have the sufficient shear reinforcements to resist the lateral loads. And finally, we have construction errors. As for the first two deficiency, they were presented in some provisions issued before in 1971, and therefore any columns detailed and designed based on such old provisions is considered deficient and must be strengthened or repaired to resist future earthquakes. So when we talk about seismic strengthening using concrete, the only way to apply this material on the surface of the column is by concrete jacketing. So when we discuss the concrete jacketing, is UHP FRC better than the normal strength concrete? By having this simple comparison, so the UHP FRC has a very high tensile strength, and that's why the jacket doesn't include any reinforcements. The UHP FRC is more ductile because it has steel fibers, and it is more durable because the nanofibers densifies its microstructure. The strain hardening behavior that the UHP FRC has make it very a viable option for applications in which inelastic deformations are experienced. And finally, since jacket reinforcements are disregarded, this means that the jacket thickness is very low, which is desired as more for aesthetics. As for normal strength concrete, it does have jacket reinforcements because the normal strength concrete has low tensile strength. It is not ductile, and it is less durable because of the air voids that it has inside. It doesn't have any strain hardening behavior. It fails after the first crack. And since jacket reinforcements are included, the jacket thickness may be increased or may exceed more than 100 millimeters, which is not desired for aesthetics, and it also changes the dynamic response of the structure resisting earthquakes. And this makes us conclude that the UHP FRC is way much better than the normal strength concrete. Actually doesn't stand or doesn't have any chance to compete with the UHP FRC. So what are the components of the UHP FRC? Starting with number one, it has a very high cement content, and this is very necessary to get a very high compressive strength. Second, we have supplementary cementitious materials such as fly ash or silica fume to enhance the fresh properties of the concrete. Number three, it has steel fibers in order to increase the ductility of the UHP FRC and to make the material possess a strain hardening behavior, because the steel fibers will be able to bridge the cracks and transfer the stresses from cracked planes into another uncracked planes. The nanofibers, some UHP FRC has nanofibers in order to enhance or increase the cracking resistance of the UHP FRC, because the steel fibers are not efficient in bridging the micro cracks, and that's why the nanofibers were introduced to do this instead of the steel fibers. And finally, we have the superplasticizers, such as the high range water reducer, which reduces the water content, and that's necessary to get the high compressive strength. Other superplasticizers might be used to enhance the airless strength or control hydration and enhance the durability of the UHP FRC. However, what are the main components of the UHP FRC is the high cement content, the steel fibers, and the superplasticizers, meaning that the supplementary cementitious materials and the nanofibers maybe cannot exist in every single UHPC material. As for mechanical strength, from table 1, we can see that the compressive strength of the UHP FRC, based on several research works done before, it can range up between 140 to 190 MPa. Some research works reported that it exceeded 200 MPa. In terms of tensile strength, it can reach up to 15 MPa's, and the bending strength, some reported 20 MPa bending strength. However, we can notice from this table that some research works included CNF and others didn't. So for those who did, they reported very interesting and important comments. For example, Lim in 2019, he reported that the carbon nanofibers or the nanofibers has no effects on the fresh properties of the UHPC. However, Jung in 2020, he made an interesting conclusion in which the CNF, if the CNF was added in a quantity more than 1% by cement mass, this will decrease the strength of the UHPC, whether compressive or tensile, because this will lead to declustering of the CNF, which will lead to more air voids in the UHPC. And that's why he recommended the value between 0.5 to 0.8% by cement mass. As for seismic strengthening applications, starting with Beshi, Meda, and Riva in 2009, they conducted the first UHPC application in which they strengthened reinforced square column with the 40 millimeters jacket along the entire height, and then they applied a lateral cyclic loading at the top with the constant axial load. They reported that the strength degradation did not start until the UHP FRC jacket detached from the base of the foundation at 3% drift, and the column failed at 6% drift due to the rupture of longitudinal reinforcements, which is pretty much amazing. Also, they reported that the lateral capacity and the ductility of the column was significantly enhanced. Another study was done by Massico and Bausch in 2011, in which they prepared a reinforced concrete column that is deficient with lap splice length, which contributes to the brittle behavior of the brittle failure of the column, because the lap reinforcements won't be able to yield or to develop a stable hysteretic behavior. So they removed the initial concrete around the splice length, and they replaced it with UHP FRC, and they reported that the jacket column was able to withstand a significant amount of displacement without any strength degradation. And this is because the UHP FRC was able to confine or to prevent the splitting cracks from occurring around the splice region, and allowing the loads to be transferred between those two bars, and thus allowing those bars to yield. And then they reported that the ductility and the lateral strength were also significantly enhanced. In Meda in 2015, he strengthened corroded column with 40 millimeter jacket along the entire column height. Then he applied a lateral cyclic loading and a constant axial load. He reported that the corroded strengthened column was able to exhibit a superior seismic performance in terms of lateral load capacity, which increased 65% more than the unstrengthened uncorroded column, and a better energy dissipation capacity. He also reported that the strength degradation also started after the jacket detached from the base, and then he ended up concluding, or he ended up with a very important thing to be considered nowadays, in which corrosion is a very serious problem which can significantly affect the seismic performance of RC elements in general. In 2016, Kuo and Hong, they studied the shear behavior of RC column jacketed with UHP FRC of thickness between 30 and 50 millimeters. They included some specimens included shear reinforcements in the jacket, and then they applied a lateral loading at the column tip. From figure 9, we can see that the strengthened specimens R3 and R5, which corresponds to 30 millimeter and 50 millimeter jacket thickness, they exhibited superior performance in terms of lateral strength, as we can see, and in terms of drift or ductility. And therefore, he ended up concluding that UHP FRC jacketing is a viable option for shear critical elements or for seismic upgrading. And then he also reported that the shear strength can be further increased by adding these steel stirrups inside the jacket, and that's what we see in the specimen R5S. There is a clear difference between R5S and the other specimens, and this is due to the shear reinforcements. And finally, Shao in 2021, he strengthened RC column with two types of jackets, UHPC jacket. The first type is the cast in place, in which he replaced the 40 millimeter covered by UHP FRC jacket along the entire column height. And the second one, he confined the column with prefabricated panels of thickness 40 millimeters made from UHP FRC. Those panels were anchored to the column, and the gaps were filled with epoxy. He concluded that the cast in place exhibited a superior performance and better performance, better than the prefabricated panels in terms of lateral strength and stiffness. As we can see here from figure 12, we can see that the C or the red line, it represents a higher stiffness for the column. And this is because the prefabricated panels wasn't able to achieve a composite action, or there was a slippage between those panels and the column, and that's why the composite action was lost or was not achieved. And this explains also that why the cast in place was able to successfully restrain the shear and bending cracks. As for the shortcomings of UHP FRC for seismic strengthening, we can notice that all works reported a jacket-based detachment, even though some of them tried to insert this jacket into the foundation through grooves. However, they still experienced jacket detachments. Another shortcoming is the achieving a composite action for such application is very hard. That's why the column surface should be treated very carefully in order to achieve a composite action or to prevent the slip between the jacket and the column. Number 3, it is a passive confinement method, and we all know as engineers and researchers that the passive confinement is not effective as the active one, because the UHP FRC jacket doesn't engage until the concrete column experiences further damage and dilation. It is a labor and time extensive because it needs preparation of the column surface, form work, and we should wait for the concrete to cure, and that's add intensive efforts and time for the strengthening application. And finally, limited ductility. UHP FRC has a very high cement content and is generally brittle, and this limits the enhancement in the column ductility. So this introduced us to the research gaps that has to be addressed in the future to make this UHP FRC a competitive material in terms of seismic upgrading of RC columns. Starting with number 1, we should implement an efficient anchorage system that can prevent the detachment of the UHP FRC from the foundation at early loading. The second point, there should be a better bond developed between the column and the UHP FRC jacket to achieve this composite action and to prevent this slippage from happening. Number 3, all the works that I presented earlier, they used the older generation of the UHP FRC, which includes 1.2 to 1.5% by volume steel fibers. However, the newest generation of the UHP FRC, it includes 2.5 or even more than 3.5% by volume steel fibers and also carbon nanofibers. And this material is still not investigated in the seismic strengthening purposes. Number 4, there should be some efforts in converting the passive action into an active action. And finally, there should be the UHP FRC should be incorporated in flexural strengthening purposes, whether for vertical or for horizontal RC elements. Thank you very much.